around page 383. You would have to fill out, if you did this thing by hand. I just want to show you what you'd have to do. You have index, you have an observed value. This would be by hand. You find this, they call it f sub I, which is equal to I minus 0.375 divided by n plus 0.25. All right. I is the index, and n is just going to be the number of observations. All right. So I just want to make a note that I in there, I equals the index that you'd have in this column, and your index would be something like, index 1, 2, 3, 4, 5, 6, 7. So you put down the index value, which is I. The observed value, like what? Like if they were gestation periods, it was like, oh, hers lasted 250 days. Then you put 250 there. And hers lasted 270 days. You put your 270 there. These would be the observed values. But then you can calculate this. I want to point out n is the number of observations you have. All right. But again, you heard me say, you're not going to spend much time on this section. It looks like a lot of math. Because we'll talk about the technology and how useful it can be. But after you do all this, you get these values in your columns, and then you get what's called your expected z-score from this. And the way you get your expected z-score, everyone, I'll give you an example of these problems. Let's say 1, 2, 3, 4, 5, 6, 7. Let's say my observed value is 245. I'm trying to think of the last answer we got. 245 point, what was it? That lower end? Is that right, Angela? 245.5. Let's pretend someone had a 245.5 days for gestation period, or 246. And you did all this math. And there are a bunch of observations. But how can I get the expected z-score for that? Right? Let's just say this math right here came out to be a 0.1. Now when I'm bypassing this, because to do all this math, I need to know what? N would be the total number of observations. I would be the index value, right?
N is 7 here, right?
Right, in this case, N would equal 7. And we'd have 7 observations. I would be the what?
1.
1. And you do all this math, and you get this value here, right? But here you got to get the expected z-score. I want you to show, well, how the heck would I get that? To do this, you'd have to hit that inverse norm button of this value. Does that make sense? So, I mean, what would come out of this? The resulting value here comes out of this little math formula. And it depends on how many values you got, right? I do want to point out, when you write down your observed values, they always want you to write them so that they're in the ascending order. So from the lowest to the highest. So if you had a group of data, let's say you had 20 data values, you put the lowest here and the highest up there. And then you do all this, then you get these expected z-scores. But I do want to point out, if you did get a value like 0.1 here, let's say, after we did all this math, you put your 1 in here, you subtract this, let's say n was a 7, you do all that math, you get a value there, but to get the expected z-score, I'd have to hit that inverse what? Norm button. Do you follow me? Because that's representing 10% from the left. Does that make sense? Hey, cool. So now, you get that, and you get these expected z-scores. Anyways, I think you all are noticing. Doing it by hand, not too bad, but isn't it time consuming?
Yeah.
This is what I want you to observe. Wouldn't that take a while? So there is software out there that can produce the norm probability plots for us. So I'm going to hit the lights, you can look at these. When I hit the lights, you can look at these. These are some examples of some normal probability plots. But these were produced with something called Minitab. Minitab, everyone, is an outstanding software. Outstanding software. But it does cost some money. So I didn't require everyone in this class to use Minitab. Although, hey, you might go take another stats course at another college, and it might be a requirement. You might go to Towson, and they'd be like, oh, to take this course, you need Minitab. Or some of you may finish your degree here, you have your bachelor's degree, and then you get your, oh, I gotta get my master's degree and take a stats course. They might say, you're required Minitab in this course. But the Minitab can produce these normal probability plots. Now when the question that's being asked here is, determine whether the normal probability plot indicates the sample data could have come from a population that's normally distributed. The answer, we'll keep this simple, the answer is going to be yes. If all these red dots, are those red dots? I'm colorblind. If all these red dots are in the curves. But if you get one dot outside the curve, we're going to say no. So how about in this image?
There's one dot all the way to the
Would
right.
we say yes or no? You know,
No.
determine whether the normal probability plot indicates that a sample data could have come from a population that's normally distributed. Yes or no? We're going to say
No.
no, because we see what? That red dot right there, right? Cool. Now in this case, in this
Yes.
problem, what could we say?
Yes.
Yes. Excellent. All
So,
right.
do they always have to have these 3 lines? Like there are 3 lines?
Yeah, and those curves were produced by the what? The Minitab software.
Okay.
And because of that, everyone, because our TIE, this thing's an outstanding calculator, does not produce those nice little curves there, Art. That's why for me, in terms of my tests, I will not require anybody to do all that by hand and stuff like that. But what I could do is on a test is take one of these images, and I could ask you what? I could give an image like this and say, hey, this was produced with Minitab. Excuse me, with Minitab. I could do that, and I could ask you, determine whether the normal probability plot indicates the sample data could have come from a population that's normally distributed, right? What would you say, Holland, in this case? No. Does that make sense? And that's important. So you go, we could do this, couldn't we? If anybody wanted to practice this, you can, and there's a good write-up on this on page 383, but without the technology to produce this, it's very, very what? It's not hard, it's just, it's time-consuming, it's tedious, true? I mean, you can even use a spreadsheet, but we'd have to produce those curves. So, and that's why I wanted to say I wasn't going to spend much time on that, Holland, because of course we can do that, but software like this really, really facilitates this. We don't have that software. So what I would do, everyone, just to wrap things up, I would produce that for you with Minitab, and then I could ask that question, right? Has everyone got it? What would you say again here? Yes or no?
No.
No. How about here?
Yes.
Yes, and then here?
No.
You got it. You got it. That's my point. Now, if you wanted to do, you're like, no, I want to do this by hand. Absolutely. Get on. She's like, no. Autumn goes, no. You get all your, you know, what are all my indices? How many do I have? Then I can start doing this. I'm with you. Yeah, we want to use the technology. It's just we don't have that here. Cool. Hey, great job. Hey, the remainder of class, we're going to spend it in section 7.4. Now, you see my title on the board? Do you see it? Oh, good. Preston?
Yeah, I have a question. So, you can't find the expected z-score without the calculator? Like, without the...
You know, that's a good question. You could use a table. I'll be honest. So if I didn't use that calculator, I could do all that math right there, Preston, by hand. Let's say n equals 7. And in this case, for this value, I was a 1. I could do all that math. But then when I got to here, I'd be like, how can I get the expected z-score? The back of your book has a card with a bunch of tables on it. You could, if you say, I don't want to use a calculator, you could read the z-score off that table. You would match it up with whatever, and then what came out here.
Okay.
Right there, I'm sorry, right there. You look, all right, what's the z-score associated with 0.1? Cool. All righty. Everyone, great job with this. I'll erase all this. Thanks, that's what I was saying. Everyone, if you're like, boy, I did not want to spend too much time on that section just because, of course we could. There's so many other great things we can talk about, especially like in section 7.4 with binomial probability distributions. Everyone, do you remember binomial?
Mm-hmm.
So binomial. Distribution. You're like, I remember this. Can we talk about this? How many outcomes were possible? 2. Success and failure. And there are a lot of circumstances, events in this world that occur such that we do have binomial probability distributions. Live, die. We talked about on time, not on time, right? I think the problem in the test was smoke before 18, smoke after 18. Hit the basket, miss the basket, binomial. Well, are binomial distributions bell-shaped?
Yep.
Are they approximately normal?
Uh-huh.
They truly are, as long as n times p times 1 minus p is greater than or equal to 10. All right? So I'm just going to make up some numbers here, all right? Here's my first example. Let's say, everyone, how about I'm thinking of like righties and lefties? Now when the probability that someone's lefty is, that's like a 13% chance. So that's given to you. Let's just say I look at 30 students. 30 students, okay? Those are called trials. Is this distribution approximately normal? That's my question. Everyone, is this binomial probability distribution approximately normal? Yes or no? Well, all we do is check n times p times 1 minus p. And we do these, we calculate it. If the number's 10 or higher, we say yes. And Holland's giving me a no. Everyone try this and go. That's a 30. What goes here?
0.13.
0.13. Some of you just do this in your head. What's 1 minus 0.3?
0.87.
Don't I go there? Now you can type 1 minus 0.13 on your calculator. I just thought I'd write like this. We're going to multiply these. Very simple. If we get a number 10 or higher, we'll say yes. If it's lower than 10, we're saying no. So sometimes the sample size is so small, and the probability is so small, it's maybe still skewed. And it's not really bell-shaped. It might look like this. I mean, it might be all skewed like that, or it might be, in this case, really low percent skewed like that. And that's what's going on. Cool. What do y'all get?
3.393, way lower.
Way, way low. 3.3, everyone, no. No.
Oh, so you can use this to see what could be a perfect sample size.
Exactly. And it's like, who came up with the number 10? You know, after all these experiments and stuff, they figured 10 was a pretty decent number for this. Hey, if you want to say this easier, everyone, 1 minus p, isn't that just a complement? You know, like, let's say there's a 30% chance of rain today. What's 1 minus p? What's 1 minus 30%? Or excuse me, 1 minus 0.3? 0.7, right? I think we should come up with a letter for the class for that. So how about from this day forward, how about in our class, let's let what's the letter after P in the alphabet?
Q.
Let's let Q, for our class, just always be 1 minus P. The only reason I'm saying that is because you might find this easier to set. See all that right there? It's an easy way to remember this. Then what would this formula be? NP Q. So you can just say, I'll just remember that NPQ must be greater than or equal to 10. How about that? It just becomes, you know, we do things like this when we're studying, practicing it. It's an easy way to remember. NPQ, greater than or equal to 10. NPQ. Q represents their what? 1 minus P. Now, and don't be shocked if for the next 6 weeks straight, I get to ask that class question every day. I'll never get mad. Student will go, what's Q again? I'll always say it, 1 minus P. So it'll come on, you'll laugh. Students always ask me, because it's not in the book, right? So students will be like, where's this Q coming from? You know, a lot of other textbooks do the same thing. That's why I'm doing it. A lot of other textbooks use that Q for 1 minus P.
If it is 89 students, then it will be more than 10.
Oh, I like this. So in my case, all right, I'm going to use a number a little bit higher than that. What if this was 100 students?
Yep, we told it.
So I went in a gigantic lecture hall, and there's 100 students there. And I want to know about this binomial probability distribution, whether that's approximately normal. Would that be basically bell-shaped? So we do n times p times, well, I call it q. And we see if this is greater than or equal to 10, and I'll put a question mark. Yes or no? And that's n times p times that q means 1 minus p. And you get your 100 multiplied to a 0.13 multiplied to a
0.87.
0.87. That's how we're getting that 1 minus p. We're just subtracting that. How big is that? Ooh, 11-ish?
11.31.
11.3. The answer is what?
Yes.
Yes. Cool. But I do want to point out for the remainder of class that when we answer these binomial problems, please, can we use the binomial method? I'll say it again. Please, let's all use the binomial method. And you go, why? Why don't you want to do the normal method and use this? Because it would all be approximate answers. Remember with this, you're talking about a discrete variable. Do you remember what discrete variable meant? Countable? And so if you're using a bell shape, which deals with the continuous variables, we're just going to be able to approximate the answer. It wouldn't be good enough. It'll be close. Plus, it takes more math. Aren't we now, it's the year 2016, we have these awesome binomial buttons on this calculator, which give the exact answer. So when we do these problems, let's all use the what? The binomial problems. So on that note, you go, well, if I wanted to approximate it, I want to have fun with that, you'd have to look at, if anybody's got, oh, you got your textbook there's here. I mean, look at page, I just want you to look at this. Look at page 390. You would have to memorize that. Seriously, that's what you'd have to do. If you wanted to use the approximate normal technique for these binomial distributions here, we would have to memorize that. And then the answers wouldn't be exact. Do you follow me? So it's, and when you know what